Many of you must feel totally not surprised because you already know what the answer should be. Why? Because we talked about this before. We said that the buckling of beam columns depends not only on the lateral loading, but it's only on the boundary condition. If we have a simply supported beam or even the beam column, the buckling load, it must be PE. That must be it. Okay. So then we found this one here. And however, what we're going to do is not only this. What we're going to do is to look at how we can use this in our design. So next question we'd like to ask, in fact, maybe the question many of you have in mind is, what makes this different? If the buckling load totally depends on boundary condition, then the next time when I have this problem, you don't even have to solve it. You just say that put down PCR equals pi square or EI over L square, right? If you, that actually could be a shortcut when it comes to the PE exams. If you notice that the critical load is always going to be the same. However, the difference is in the deflection. The deflection will certainly be different. And that's why we use this. We try to express the maximum deflection in this kind of form so we can compare the value of the maximum deflection with axial force versus the one without an axial force. And this way you can see the effect of axial force, which is also the effect of buckling, because buckling is caused by the force P. When there's no force P, there's no buckling. So the second term, you can call it the buckling effect. Now, in structural stability, the first coefficient is what we call the linear effect, or the linear order deflection, which is this one here. This is the linear term.
Professor?
Yes.
Shouldn't it be WL to the power 4? 5 WL to the power 4?
Yes.
By 384.
Thank you very much. Yes. Good catch. Thank you, Tech. It's WL4, right? So please correct it. And the second part, it's what we call the nonlinear effect. And nonlinear effect in this case is what the buckling force does to the maximum deflection. So you can say this is due to buckling. And the linear term is due to what? Due to lateral loading. In this case, is the uniformly distributed load. Now we'll come back to look at to better look at this expression. Now, in the design, if you want to use it to calculate that, what will be the maximum deflection? Why the maximum deflection is important? Because in structured analysis, we have usually two different criteria to consider. The first criteria is we call force criteria, or not force, sometimes we call strength criteria. I think that's more appropriate. And the other one is what we call compatibility criteria. Today, in all structural designs, both criteria must be considered. Strength criterion is very simple. It's just to to make sure that your maximum stress that's from the materials must be greater. Let me rephrase it. The maximum stress caused by the loading must be less than the maximum strength. And the strength for ductile materials, we call it sigma y. So when we write maximum stress, sigma maximum is less than sigma y. That's when we apply strength criteria. What's compatibility criteria? Compatibility criterion is to say that the maximum deflection, in this case is buckling, that's delta, must not be, which we use the same symbol. So let me just change back. Okay. The maximum deflection here must not be greater than the maximum spacing or the maximum allowable displacement that this particular structure member can exhibit. And that's, you can use this delta to define it. So sometimes when we look at the maximum deflection, Y max, we want to know that what will be the maximum Y max when we consider a beam column member. Because the difference between beam column members, as we established already, is not because of the critical load, but it's because of deflection. So we will use this buckling expression here to check that what will be the maximum deflection for beam columns. And to do that, 49, we can use another mathematical technique called Taylor expansion. And we will use it several times, but this is maybe the second time we use it in structural stability. So what we're going to do is this. We will look at the expression of the one we had before, and which is this one right here. And suppose we call the linear effect, this coefficient, we call it Y naught. We're going to call this one to be Y naught because it is the linear term and is the maximum deflection of a simply supported beam subjected to uniformly distributed loading, no buckling force. So it's this value. So we can say that this equals to Y naught times something like that. And then we know that Y max equals Y naught times this whole thing, which is 12 times 2 times second u minus u squared minus 2 over 5 over u quadruple, like this. And mathematically, we can approximate this expression because sometimes you have quadruple in all these terms, they may not be that easy to be used. So in the past, we usually like to give engineers some simplified expressions for them to use. And from Taylor expansion, you can second u can be written as the summation of this infinite series, which is 1 plus 1/2 of the u squared plus 5 over 24 times u quadruple plus 61 over 720 times u to the power of 6, and that should be enough. Now, mathematically, there are also terms we call them in any Taylor expansion of any sinusoidal functions or even exponential functions. The first one is, as you already know, we call it linear term. And everything else we call it higher order terms, which is hot. Now, the number of the higher order terms is decided by the required accuracy in this approximation. So if you just want to get some idea about how close, well, I just want a number in the ballpark, then all you need to do is just to take the first higher order terms. But if you are designing some kind of structure, you really need to get very accurate numbers. So perhaps you should include 2 or even 3 higher order terms from this expansion. Right? But the rule is when you observe this function, the first question is, do you think this function, in this case, is second U, right? Do you think this function is linear? Do you think it's linear? Of course it's not linear, right? None of the trigonometrical functions is linear. Sine is not linear, cosine is not linear. Neither can second U be linear. If none of them is linear, which means you must consider at least one higher order term, at least one. That means the minimum one is you must have this. Consider. Otherwise, your expansion is just wrong. If you consider only linear term, it's wrong because second U is not linear. Okay? And so from here, we can expand it and we can write that Y maximum can be approximated to Y naught, which is that coefficient, times this expression, which is 1 over 1 minus P over PE. And this kind of equation is usually used in the design. So this is for design purposes. In other words, Y naught is just a constant. You can take it from the textbook. And when you want to calculate the maximum deflection with the buckling, all you have to do is to find out what is the current load that you have in this P, and you plug in this expression, and you can calculate the amplified maximum deflection. So this is not the one without the force. This is the one, remember, we have the buckling effect considered. So you use this calculation to check the compatibility requirement or to check that whether your design will meet the compatibility criteria. Okay. And similarly, I will not going to give you the derivation, but I will just give you the result. What about the maximum moment? And this is for deflection. What about moment? It is true that the buckling load will not be amplified by lateral loading, but the moment will be amplified by lateral loading. Okay? Now, understand the fundamental difference between, this is important concept, which is the one without lateral force and the one with lateral force. Suppose we use this one because we are discussing this case. The governing equation for the first one, we already know it very well. That is Y double prime plus K squared times U is 0. Right? But for the other one, it's not. That is Y double prime plus K squared times U equals to W x squared over 2 minus WL x over 2. Is this that we had from before? So the difference is this term right here.